Hello, Tizzler friends. I needed to answer a question that I asked myself because no one else will talk to me. What exactly is a geodesic? What are we talking about here? Okay, definition. On a Riemannian manifold, a geodesic is defined to be a curve whose tangent vectors remain parallel as if they are transported along it, right? So parallel transport is moving a vector along a manifold while trying to keep it as parallel as possible. That's what parallel transport is, okay? What is a condition of parallel transport? Well, the necessary condition is that the covariant derivative of the vector component of that vector's components be equal to zero. Okay, and a quick review. The covariant derivative of a contravariant the vector component is equal to the partial derivative, and this extra piece, which accounts for the fact that the basis vectors may be varying on the manifold, and in the case of a sphere, they're varying all over the place. Okay, so the condition of the covariant derivative being equal to zero then puts this equation equal to zero. All right, now we want to look at what happens on the two sphere, where we're only looking at the surface, the coordinates theta and phi. The radius, we're going to call a, is a constant. It's going to be held constant, okay? So we're going to have two variables. And what we're going to do is we're going to look at two different cases of parallel transport where theta, this angle, is going to be held constant at two different values, and we're going to look at the parallel transport. So here's the equation we have to deal with. All right, so let's expand it, and you see that we have two free indexes, I and j. Here they are, I and j, and k is our summation index. So in the first case, we're going to choose the derivative of the theta vector component with respect to phi. So our free indexes here are theta, phi, theta, phi. Our summation index in the first case is theta, the second case phi. Now we do the same thing for the theta, the vector component with respect to phi. So we're differentiating this with respect to phi. That's the point. All right, so we fill this in the same way we did this when we got two equations here, okay? Now, here are the non-zero Christoffel symbols for the two-sphere, the problem. Okay, we got three of them. So in this first case here, we got theta, theta, phi. Do we have one of those? Theta, nope. Do we have one of these? A theta, phi, phi. Yeah, right there's one. Okay, so we got a hit. So we put that in. Now we got an equation. Now let's look at equation number 2. Do we have a phi, theta, phi? Right there. We do. All right, so we got another hit. So we put that in. So now we've got two equations here, which are the coupled partial differential equations. Why are they coupled? Because there's a v theta here and a v theta here and a v phi here and a v phi here. So these are coupled partial differential equations. So you have to solve them at the same time. Okay, so what we can do with equation number 1 is we can differentiate that again with respect to phi. Okay, so we're going to differentiate that again with respect to phi. And so we get the second partial derivative, and then we get this term. Now you're saying, well, there's two terms here. Shouldn't you use the product rule? Yes, except there's no phi components here. So the differential of this with respect to phi is 0. That's why there's no second term. Okay, I asked myself the same question when I was looking at this. All right, so now we've got an expression with this in it, and let's look at equation number 2, which I just took this to the other side. That's all I did. So now we have this. So I can put this right back in here, and we get this expression. Okay, so now everything in this equation is theta. Now let's do the same thing with equation number 1. Oh, I simplified it. The signs cancel, cosine squared theta. Let's do the same thing to equation number 2. We differentiate it again with respect to phi. We get this expression. we take that from equation number 1. So I took this to the other side. I'm going to put this right back in here, right? And I get this, I simplify, and I got that. Now we have two even more complicated equations because they're second order differential equations. And they're not coupled anymore. So these are just ordinary differential equations, and you may recognize them immediately. The solution is the simple harmonic, the motion, right? So if you had a block on a spring, you would equate Newton's the second law to Hooke's law, and you would get the concept as these equations. And the answer to these equations, a miracle occurred, and here's the answer. Okay, is simplified to this. Now, these constants out front here, where this comes from is that the basis vector E theta is magnitude is A in our case, just because we only got the surface of a sphere, and its magnitude is A, so that gets rid of this. The magnitude of the E phi basis vector is A sine theta, which gets rid of this. That's where these two things come from, the initial conditions, okay? And omega is defined as cosine theta. It's a constant, okay? We're going to look at two cases of it. Okay, now we have a vector, and we've expressed it in terms of theta and phi. So we just found these two things are this and this. Now we need our basis of vectors, and I'll leave a link to all this stuff where this comes from. It's all over the internet, but I have it in a playlist. All right, so here's the E theta basis vector. Here's the E phi basis vector. So we're going to put all that back in here plus the two equations we found. And you get this mess, which you crunch, algebra. Okay, now we have what we want, which is this vector in terms of theta and phi that now we can graph. So let's go look at that. Okay, here we go. We got a sphere. We got a point on that sphere, which is a function of theta and phi. The radius is held constant, okay? Now, what we're going to do is define a tangent plane at that point, okay? There's a tangent plane at that point, and on that tangent plane, we're going to put the vector that we just did in the document. So this is the vector in a tangent plane at that point, okay? I'm going to get rid of the tangent plane because it gums everything up. So what we're going to do is set theta equal to 60 degrees approximately. There it is. And now I'm going to set phi in motion. So look what happens to that vector as it goes around this sphere. See it changing directions all the time? It's doing that because it has to stay in that tangent, the plane, right? So it's having to change all kinds of funky positions to stay in that tangent plane. All right? So now let's stop that and let's move theta to 90 degrees. Look what it did in a tangent plane. Now watch this. Let's put phi in motion. It's staying right where it is all the time. Okay? So that is a geodesic because it is staying parallel at all times. Okay? Wasn't that fun? See you later.